everyone, Mrs. Patel Dame here for topic 7.9, Introduction to Le Chatelier's Principle, and topic 7.10, Reaction Quotient and Le Chatelier's Principle. So by the end of this lesson, you will identify responses of a system at equilibrium to an external stress using Le Chatelier's Principle. Pretty much when something happens to your reaction, is it going to go to the reactants or the products? And then what also happens between K and Q and which direction the reaction is going to go in equilibrium to respond to that stress. So here is actually a demo I did in my kitchen. So I took regular household mustard and I went ahead and added a base to it. So it looks like color red. Then I added an acid to it, went back to mustard color, base, back to red, acid, back to a mustard color. So I did this back and forth. So this shows you that even with the same system, it can go back and forth between like one color essentially versus another color just by adding something in. So that's one type of stressor, changing in concentration. We can also add other stressors to our reactions by changing its temperature or its pressure, but that's only for gases. So throughout this video, I want you to kind of imagine a seesaw. We're going to use this little demonstration down at the bottom in order to show you that. I also suggest that students use a pencil and kind of think about like, okay, if I were to adjust one thing on one side, what would happen to the other side? That pencil really helps out when it comes to your test time. So on this seesaw, we've got two little blocks. What would happen if we add a second block on the left-hand side? We can imagine that being the reactant side if we need to. So as we know, the left-hand side will essentially go down. It now favors the right-hand side or the product. So try to think about that terminology, favoring the right-hand side. It's whatever side would go up if we're thinking about the seesaw. So if we added another block, it would balance out and come back to equilibrium. Now, if we added a third block to the right-hand side, we think about, okay, so the right-hand side would go down, the left-hand side would go up. And so that means that it's favoring the reactants or the reverse direction of this reaction. So if we want to kind of bring it back to equilibrium, we'll add two blocks, or we'll remove that block and kind of bring that and establish that equilibrium. So again, think about that seesaw. So we have this reaction, N2 plus H2 is in equilibrium with NH3. We have heat on the right-hand side as well. So we have to balance our chemical equation. And let's think about this again with that seesaw. In this case, the little seesaw, the little things are at the bottom instead. So we have 1 mole of N2, 3 moles of H2, 2 moles of NH3, and we have 22 kilocalories of energy. So what would happen if we added N2? Think about this and use, again, your pencil to help you kind of figure this out. So if we were going to add N2, that means that the left-hand side would go down, and that means it's favoring the products of the forward direction. So essentially think about this as if you add more N2, it's going to use up some of that H2 to make more NH3 or drive the reaction towards the products. We also think about our K value. Since we have that same ratio, the K value itself wouldn't change. We'll reset it, and then thinking about what if we added H2. Again, use your pencil or your pen and think about that seesaw. As we add H2, it's going to use up more N2, to make more NH3. So if we're going to add NH3, we're going to drive this towards the reactants. So that NH3 is going to break up into N2 and H2 in order to reestablish equilibrium. Again, your K values are staying the same. So if we do the opposite, remove N2. Now think about what would happen on your seesaw. That NH3 would end up being broken up to produce more H2 and then N2 to overcome the fact that that initial N2 was being removed. Again, if we remove H2, it would drive this towards the reactants or favor the forward reaction in order to, again, make more H2 and N2 to make up for that missing H2 that was removed. If we remove NH3, those reactants will then go towards the products or combine in order to make those products. Now, if we play around with temperature, so remember, temperature is not the same thing as heat. Temperature is average kinetic energy. Heat is the transfer of energy. But we're going to use this as part of our demonstrations. I want to make sure that you guys remember the difference between the two. So if we double the temperature, think about adding another weight on that right-hand side. We would drive this towards the reactants or the reverse reaction. If we did the opposite, decreasing the temperature, we would kind of remove that weight from the right-hand side and then drive this towards the product and, again, make more of that product. Now, if we played around with pressure, this is a little bit harder to show you when it comes to like a seesaw like this, but instead think about the number of moles of your reactants versus your products. On the left-hand side, we have 1 mole of N2, 3 moles of H2, so a total of 4 moles on the left-hand side, and then we have a total of 2 moles on the right-hand side. So if we increase pressure, the volume itself of this the vessel would decrease, right? So what would fit? Something that has more moles or less moles? So in this case, of course, it's going to be the one with less moles. So if we increase the pressure, we're going to favor the side that has the least amount of moles. So in this case, it's the NH3. It's not necessarily always going to be the product or always going to be the reactant. It's just based upon the number of moles. If we decrease the pressure, meaning increase the volume, we have essentially more space for those moles to fit. So we're going to drive this towards the reactants. So this is a demo I have where I have cobalt-2 chloride and I added some calcium chloride to it. You can see that the color itself has changed. Now I'm going to take the test tube on the right-hand side and it has like this little purplish hue to it. And I'm going to distribute that amongst other test tubes and change up the conditions. So here I've got 5 test tubes that are a little purple and then that one pink one just to show you that initial one. I'm going to put it in hot water, in cold water, and then we're going to go ahead and kind of play around with the other substances as well. So we're going to add, in this case, more of the calcium chloride that we had in there and see what ends up happening. So adding more calcium chloride. You can see that the color's changing slightly. Of course, the light's a little bit off, but now has a blue tinge to it. And so we've seen, again, a difference in color change. We'll take another one, and in this case, we're going to add silver chloride to it. So thinking about silver nitrate to it, that silver is going to actually combine with the chloride ions that are in there and then form that precipitate. So we'll go ahead and check on our cold one. We see that change from that purple color to more of a pink color. And you can see this automatically with the one that we warmed up. What was purple has now turned to blue. So we have to think about what might happen with that. I want to show you what actually happened with that blue one if we let it sit at room temperature and then added a little bit of cold water to it. Of course, I don't want to take that hot test tube and put it in cold water because it's going to shatter. But you can see that I can change the color essentially based upon the types of the temperature itself. So this is what it looks like. I've got the pink, the purple, and the blue. The pink is the cobalt hexahydrate, and I've added chloride ions to it. That produces cobalt 4 ions, or cobalt 4 chloride on the right-hand side. So when you know you have more of the left-hand side, it actually ends up being pink. If you have more of the right-hand side, it ends up being blue. What's in equilibrium is purple, if you think about your color wheel. So if we think about our concentrations, if we increase the concentration, it's going to favor whatever the opposite side is and doesn't affect K. So if we added more chloride ions to this, we see that it turns to be more blue. We've added more chloride, we've driven this towards the products, and so we've favored the products in this case. If we decrease the concentration, then it would favor that same side, and of course it does not affect K. For endothermic reactions, we would say that in this case, this is an endothermic reaction. We started out with the system at equilibrium, and we can kind of think of heat as being in the reactants. So if we're going to increase the temperature, it's going to favor the product. So again, use that pencil to help you with that seesaw aspect. And so again, it's driven towards the products, we're making more cobalt 4 chloride. And the opposite, if we actually took that system at equilibrium, added ice to it, we see that it becomes pink. We've driven this towards the reactants, the cobalt hexahydrate ions. So think about that for endothermic reactions. For exothermic, it's going to be the opposite. If we heat's going to be in the product. If we increase the temperature, it favors the reactants and decreases your K value. If you decrease the temperature, it favors the products, it increases your K value. Change in temperature or addition of or subtraction of heat is the only thing that affects your K value. If we think about pressure, again, gases only, we're going to go back to that N2 and the H2 that we had dealt with before. That's the Haber process. Look at that. It's actually one of the most important reactions I personally think that our world has. And so if we increase the pressure, we know that we have a larger amount of volume. It's going to favor the side with the least number of moles of gases. If we decrease the pressure, however, so we're if we increase the pressure in this case, we're decreasing the volume. We're going to favor the side again with the least number of moles. That shows you that it's NH3. So just to kind of repeat myself, N2, you have 1 mole of that, 3 moles of H2. So you have a total of 4 moles on the left-hand side. You have a total of 2 moles on the right-hand side. So when we increase the pressure, we decrease the volume, and that's what this looks like. We see that we can favor this. We favor the side. If we increase the pressure, decrease the volume, we favor the side with the least number of moles of gases. That's what we have here. If we decrease the pressure, we increase the volume, we favor the side that has the most number of moles of gases. So again, make sure we have this part of it here. This system is showing that we have a greater volume, a smaller amount of pressure, so we can have more space, essentially, for all of the more moles of gases. This system is showing us that we are going to increase the pressure, decrease the volume, have more space for the side that has, or have less space, for the substance. And so we're going to favor the side with the least number of moles of gases. So K versus Q. Pretty much when you're thinking about this, again, think what K values are versus Q values. K is going to be the system at equilibrium. Q is going to be what and when it's not at equilibrium. So if your K is less than Q, we're going to favor the reactant side in order to establish equilibrium. If K is greater than Q, we're going to favor the product side in order to establish equilibrium. Again, we're changing up Q in order to match up what K would be. So you can, of course, think through the math for this as well. If you have any questions, let me know. Thank you to chemmix.org for our wonderful demos. Have a great day.